Okay, so I will speak today about, I gave a title, Boiling QCD. This means boiling, boiling water is the first order phase transition, from liquid to gas. So I will speak a bit about a first order phase, that this transition, which we discussed in the last lecture, from nuclear matter to quark matter, may be a first order phase transition, like boiling water, with a lot of latent heat involved. And maybe you will be the generation who will construct the new steam engine on the basis of quark matter. Okay, I will then present you also such a steam engine on the basis of quark matter, which is a massive supernova explosion. So the energy for the explosion of very massive stars, 50 solar masses, so I can change slides here, will be, this I want to show you, will be provided by the deconfinement of quarks. And we will also speak about then these events. This is just an artistic view of how two neutron stars, which form a binary, emit gravitational waves, lose energy, and come closer and closer, and finally they inspiral and form an event which is called a kilonova. Kilonova because it produces the energy of 1,000 nova explosions. Okay, but before that, I was asked today to say something about Mendeleev's table of elements, because we have the 150th anniversary of the announcement of this periodic table of elements. And then, of course, I would like to iterate a little bit on this topic of elements in the context of astrophysics. And here I make 3 points. I shortly review with you what we know, or what we seem to know, about element synthesis in the very early universe, the Big Bang nucleosynthesis. Unfortunately, so far, best we know is that only very light elements are formed in the first 3 minutes. And all the remaining elements have to be formed in other cooking pots. And one of those cooking pots for heavier elements, where element synthesis by fusion of hydrogen, helium, and so on takes place, is the stars, the main sequence stars, also the heavier stars. And finally, there is an endpoint for such element cooking around the iron group elements. But we know you have gold, silver, uranium, and all these heavier elements. They are there in the cosmos. Where do they come from? And here for a long time, the paradigm was that we could only imagine, supernovas. Supernovas produce a lot of energy, and they produce also some neutron fluxes, and hopefully in this way also the heavier elements could be formed. But now we are convinced, and we have good indications for that the real site for the very heavy R process, so-called rapid neutron capture process, elements to be formed, are the mergers of compact stars. So this will be mainly the context of today's contents of today's lecture. Okay, let's start with Mendeleev. It was on March 6th that the periodic table of elements was presented in the Russian Chemical Society. It was actually not presented by Mendeleev himself, but by one of his collaborators. And this is one of the historic old versions of it. So you see elements grouped up to 8, and the key was that one had measured already masses of the atoms, and then one could order the elements by their atomic mass. And then the chemist, like Mendeleev, he noticed that there's a periodicity in the chemical properties. After 8, there was a repetition of the properties. Yeah? And this led him to make an order scheme like a table, where with 8 columns, and then was a new row. The rows were called periods because of this periodic behavior of the chemical properties. Later on, this gets a little bit more complicated, we will see. But this was the main thing. And first, of course, he was criticized by that there were holes in this table, so there were unknown places. No elements filled that table. And actually, this turned into the big power of this table, of this systematics, namely that Mendeleev could predict new elements, which were not known at that time. He called them eka. So eka means that you go from one place, here for instance aluminium, you go one period below eka. Then here he suggested eka aluminium. And now aluminum, so now we know this is gallium, was later found. Eka boron was then became scandium, and eka silicium became germanium, and there were more such empty places which by now are all filled. And this is a modern view on the Mendeleev's table, and you see we have now 7 periods. And the last element, so actually the 7th period is now filled. Last element is called organeson. This is Yuri Tsalakovich Oganessian. He is the only still living person on Earth after whom an element is named. And he lives in Dubna. And of course the question is then, what next? Is there an 8th period? Yeah, of course, there is no reason that the size of elements should somehow stop, although these elements here are extremely short-lived, and it takes all the art of experimental physics to detect and also to prove their existence. I will not go into the details, but just mention that in Dubna, the success story of finding super heavy elements will be continued. The good precondition for this is the building of a super heavy element factory. So now we have the possibility to produce enough, so to say, events in a certain given time span, so that the probability of finding still heavier elements, provided you have the correct ingredients by collisions of less heavy elements to form new super heavy elements, this is the precondition, is to have this accelerator machine for these heavy elements. Yeah, and we're of course proud that the names also reflect this work of Russian scientists. So in particular, we have element 105, is dubnium. We have moscovium and stopiat. So stopiat is dubnium. And we have also fluorovium. Here, 114. Fluorov was the leader of this laboratory before Oganessian in Dubna. Okay, now Mendeleev, of course, I wanted to of course tell this story about Mendeleev's PhD thesis and the importance for the production of vodka. Like everybody knows, everybody has heard this story that which is half true, but only half true. So Mendeleev indeed wrote a PhD thesis on the mixture of alcohol with water. And but everything else is then a myth, the myth that he found that the optimal mixture is of alcohol and water is 40%, and then he became member of the Russian Commission for production of vodka, and that by the law that it was set to 40%, the alcohol volume percentage in the vodka, because in his PhD thesis actually he worked on the mixtures where the percentage of alcohol was above 70%. So he had nothing to do with the 40%, and actually this decision that vodka should have 40%, and in any case not less than 38%, otherwise the sellers of the vodka would be persecuted. This was adopted already in the year 1843, I think, and at that time Mendeleev was just in school. He was 7 or 9 years old. So much to the myth. So if you hear that somebody tells you, until yesterday I also told many times that Mendeleev invented these 40%. That's not true. But it's a nice story, and as all nice stories, they get told again and again. Now, after this overview over heavy elements which we know to exist, now let us ask the question where they come from. We go to the very early moments of our being, of the cosmos, of the universe, and we are convinced, so that's our best of our knowledge, it's the Big Bang Theory for the origin of the universe as we know it by now. So now it's here, this is today, and when we go back to the past, so something like 13 billion years, we come to a very hot early stage where everything was just energy, so just light, and light had so much energy that it could pair create particles and antiparticles, and these antiparticles annihilated again into light, and this was an equilibrium of light and matter. When you put in corresponding equations of state and Einstein's general relativity equations, then you find out that the universe cannot be static, so it must evolve. And if there are so-called condensates involved in the evolution of matter, so mean fields, then some stage of inflation happens. So this is an exponential blow-up of the spatial distances. And this is important for understanding why nowadays, and also in this later evolution, the universe is practically flat. So there is no clear indication for a curvature, although we know that in the very early time when the first droplet, the first atom of our universe was there, the space-time was very much curved. But this ended after the inflation, as we believe. At that time, the matter content was just quarks and antiquarks, and you see here light quarks, you see also top and antitop, so the very heavy quarks. You see the corresponding gauge bosons, which are responsible for the interactions, so gluons, photons by these wavy lines, W bosons for the electroweak interaction. And after a further expansion and cooling of the universe, then the equilibrium between matter and radiation was disturbed, and finally there appeared a point when electrons, and so when first the quarks became confined into nucleons. So this is here. Here is still the quark world, and here is the world of nucleons and nuclei. So after 100 seconds, so this famous first 3 minutes of the universe, after 3 minutes, the first elements formed. And what has been formed is proton, neutron, and from protons and neutrons you can form deuterons. Then tritons is a heavy form of the hydrogen, and finally helium. And then that was it, basically, because there's a problem with the formation of further elements. So at this point, at the first 3 minutes, the element synthesis was switched off. So this is actually, okay, here. So this is the lower corner of the table of the nucleides ordered by neutron number and charge, so proton number. We have hydrogen, so the very lightest elements. Then the heavy hydrogen, which is deuterium, so in the nucleus is a neutron and a proton. So therefore we have one neutron and one proton here. Then we have 3 helium, so this is 2 protons, but only 1 neutron. And then 4 helium is a very stable element, 2 neutrons, 2 protons. And then just a few elements of lithium could be formed, but all the others not. And why? Does anybody know why the element synthesis in the early universe stopped at that point? Say once more. Well, so we have, imagine, we have the universe, still temperatures are, well, here are the temperatures, 10 to the 9 Kelvin, so we have, 10 to the 9 Kelvin, so this is about an MeV of mega electron volt of temperature. So why could not, for instance, hydrogen or helium and lithium form the next heaviest element? So 2 times helium would be 4, and 4 would be beryllium 8. Why beryllium 8 is not formed? So the point is the following, that and this is called the deuterium bottleneck problem. The deuterium is very slightly bound only. The binding energy of deuterium is only 2 mega electron volt. So for not being destroyed again in the evolution of the universe, the temperature had to fall to just less than 2 MeV, so actually less than 1 MeV. And that was then too cool, so there's then too less thermal energy in the hydrogen and the helium to fuse to heavier elements. And we needed the deuterium to create then in binary collisions the tritium and the helium. So once the helium is there, then the universe unfortunately was too cool to form heavier elements. So that is called the deuterium bottleneck problem. And maybe you invent something clever to get around this. It would be nice to have a theory where heavy elements could be already formed in the early universe. Why? Because when we look at the oldest stars in the universe, then we find in all of them traces of heavy elements. So there is no so-called population 3 stars in the universe, which consist only of these primordial elements. And to explain this, one possibility were that the element synthesis in the early universe happened in a bit different way, so that also some traces of heavy elements could be formed. But at the moment, we have no idea how to do that. So this is how the time evolution then looked like. So here is time in seconds, and the lower axis is temperature in Kelvin, kilo electron volt. So temperature falls here from 1 MeV, here's 100 keV, keV, and so on. So first, so look, we have hydrogen, and the red line which you can follow is the deuterium. And only when it becomes cool enough, so when the temperature falls below 1 MeV, then sizable amount of deuterium can be generated by fusion, so that it does not get destroyed again. And once we have deuterium, then all the other elements come up here in a certain amount. So, and these are then the fractions of the elements. 1, 100ths, 1/10,000ths, and so on. So it's an exponentially falling behavior with the mass number. And this is how these predictions of the Big Bang nucleosynthesis compare with the observations. So actually one of the variables and also measurables in cosmology is the baryon to photon ratio. So what does it mean? So when we follow here again the evolution, then there is a point when electrons and positrons annihilate and form when the electrons get captured by the atoms. So here, this universe up to this point is still electrically charged. So we have free electrons and we have charged atomic nuclei. So positively and negatively charged particles. So it's a plasma. And a plasma, like a flame, is opaque to light. So the light cannot freely penetrate through this plasma. So the mean free path of a photon in this plasma is very short. But when the temperature falls further to the range of electron volts, yeah, then the electrons can be captured by the atoms. We have a neutral universe of atoms, so symbolized here by these logos for atoms. And in a neutral universe, the photons can propagate very far. And actually, they can propagate from this point on of the last interaction with matter up to our modern detectors for the remaining billion of years. And this is actually, so this border here of the formation of neutral atoms is where the cosmic microwave background radiation that we measure now has been, so to say, decoupled from matter. And the fluctuations measure the fluctuations of the matter density at this point in the evolution of the universe. Okay, so from then on, we had photons. The photons were generated themselves by the annihilation of matter-antimatter, and we had a remaining slight asymmetry. Therefore, we are sitting here. Otherwise, there would be only light in the universe. There was a little asymmetry of matter over antimatter. And how much? This is a very small number. So actually, it is a number measured in units of 10 billion, so 10 to the 10. So there are 10 to the 10 more photons around than baryons. And in other words, for 10 to the 10 antibaryons, there were 10 to the 10 plus 1 baryons. So you can imagine all these zeros, yeah? So this was the amount of asymmetry in the early universe. So it was highly symmetric, so up to the 10th position after the comma. But then was one more atom or one more baryon than antibaryon. And this is why we are sitting here. We are made from this one extra baryon per 10 to the 10 antibaryons. And also by the same reason, we are flooded by photons, these microwave photons. About 400 or 500 per cubic centimeter per second. And about the same number of neutrinos go through us all the time. Okay, so we have this number. So this number we measure. We can count the protons nowadays in the universe. This is 1 proton in 1 cubic meter in the mean. And we know this cosmic microwave background temperature. Therefore, we can estimate how many there are. And the ratio is this 10 to the 10. And now we compare, as a function of this variable, what this Big Bang theory would predict in elements. So here, these are the 3 yellow bands for helium-4 observation, for hydrogen, and for deuterium observation, and for 7 lithium. And so you see, when the baryon-photon ratio was this number, then, okay, so this is the prediction, the blue line, very nicely hits here this tiny yellow box. Also, this prediction very nicely hits here this yellow box. But the prediction for 7 lithium is off. So it does not match here this yellow box of the measurement of 7 lithium. There's a 7 lithium problem in the early universe Big Bang synthesis. So still work to do, and that's the same. Now let us move on. Actually, if there are questions, I'm very much in favor that you ask questions when they appear. So you can interrupt me anytime. So if you don't interrupt, then I understand that you understand everything. So don't hesitate. Just raise the finger and then ask the question. Okay, no question up to this point. Then we go on. We would like to understand where the other elements come from. So then, going back to our cosmic evolution, let us see where we are here. So we have these light elements, and then universe was neutral, and then gravitation could play a role in the neutral universe, and the density fluctuations then could by gravitation be clumped to stars, to star associations, to galaxies, black holes, and so on. So now, when we have stars here, then in these stars we have first only hydrogen, helium, and then under the gravitation, the stars can cook the elements. And for cooking elements, it is important that you can gain energy. If you would not gain energy, then the process would not happen. And so here you have to look what is the binding energy per nucleon. This is something which we discussed yesterday. So for different elements of different mass numbers A, and we see there's a maximum. And the maximum is around iron. So anytime we make a fusion, so let's say we go from 2 hydrogen to deuterium, or we go then to helium, then we gain some energy. And this can go on up to the point of iron. Then by putting more particles on iron and fusing with iron, we would go here, and then we would have to invest energy. And that does not spontaneously happen in stars anymore. So the element synthesis in stars stops at the iron peak, in the iron group, with the iron group elements. So this is roughly the cycle, the life cycle of stars. So by their gravitation, some clouds of atoms then form first protostars. Finally, the hydrogen burning is ignited in the very interior. Hydrogen burns to helium, and then you form more and more helium. And finally, if the star is large enough, it has enough gravitational energy so that the conditions in the very center of temperature and density are sufficient to fuse also helium. 3 heliums make carbon, for instance. So carbon is very important for our life. Without carbon, we will also not sit here. Carbon hydrates form all the living cells and so on. Yeah. So finally then, those stars become unstable, and depending on how massive they are, there are different evolution stages. Interesting for us, of course, are the supernovas. They are magnificent events which produce the nebulas, which can now, after many hundred years, be seen even by telescopes. And in some of their centers, we find neutron stars, because in this collapse of a big star, then matter can be so much compressed that the atoms get compressed to one big gigantic nucleus. And that is what a neutron star is. It is a gigantic nucleus, and you have heard about this in last week I'm sure that David Alvarez explained this, and Howard Gregorian told you how these neutron stars cool. If the mass, and they also told you that there's something like a maximum mass, and when there is too much mass involved, then gravitational collapse cannot be prevented, and you form black holes. There are also other events of final stages when not a neutron star, but rather a white dwarf is formed in the evolution. Now let us, yeah, so here we have now understood that at the end of this cycle of star evolution, we have iron. But when we remember Mendeleev's periodic table, where was iron? Iron was at the very beginning. Yeah, it is here, 26. So that is just the period number 4 in the middle. So there's a long way to go. All these elements would not exist if there were element synthesis only in the early universe and in stars. So therefore we have to discuss with you now, where do the other elements come from? And of course, one hypothesis is that in this supernova explosion, that there are temperatures and densities involved which could be sufficient to cook heavier elements. So a supernova is started when a star forms an iron core. So you have iron, and then you have a gravitational instability. The star explodes, and then iron can meet hydrogen and other nuclei on its way. And in this way, you could fuse, by having enough kinetic energy, you could make the fusion, which otherwise would not be possible. But calculations have shown that you come only a certain way, but not to the very heavy elements. And nowadays, we are convinced that these events are the sites for forming the very most massive elements in Mendeleev's table, when namely 2 neutron stars, or 2 compact stars, are inspiring because they lose energy from emitting gravitational waves, so over billions of years, or millions of years. Then finally they come closer and closer, and when they are, then the final merging event, the in-spiral, takes only a few milliseconds. And after these few milliseconds, you take, for instance, 2 neutron stars. From 2 neutron stars of a typical mass, like David Alvarez explained you, 1.3 solar mass, 2 is 2.6. And 2.6 is already beyond the stability, beyond the maximum mass, which you have seen in David Alvarez's talk. So a black hole will be formed. But since in this in-spiral a lot of angular momentum is involved, so a lot of centrifugal force, this very massive and very hot star can still live for a few milliseconds before finally collapsing to a black hole. And these are the decisive moments when here in such a merger event, so this is a simulation, when there are conditions formed in, of temperature and density which are sufficient to form the very heavy elements. And here it plays a big role that the cooking ingredients are neutron stars, are these gigantic nuclei made up practically only of neutrons. And when you have neutrons, the neutrons can decay to protons. You can form practically nuclei of any size. So even those nuclei which we cannot synthesize in the laboratory. The problem is only what remains, because the super heavy nuclei, they are so short-lived. And to observe them in such an event, that would be fantastic, but at the moment we have no clue how to do that. So we can be convinced that there are very, very heavy elements, but we have not yet the means to detect them. So okay, so here we have a sketch of atomic mass number, and you see we have iron was somewhere here. So this is after iron. So here are different peaks, the so-called R-process peaks. And we form lanthanides, actinides. These are these groups in Mendeleev's table. And they are the key elements which otherwise could not be nicely formed. And so here we have a comparison with experiment, I say. So here we see the very massive elements and the rates with which they are generated. And so we can conclude that in these merger events, so actually in these outskirts, there are the super heavy elements are formed. Then what to see from this event? First, we have a very dense system. The photons cannot be emitted, so the system is opaque to photons. But with time, the system expands and cools, and the mean free path of the photons becomes longer, and they can escape. And then we can see them. And therefore, there are then, depending on the temperature, the photons have a different spectrum. They are more blue when it's more cool, or they're more red when they are emitted while the matter is more hot. And so now this is the real event. In gravitational waves, 2 years ago in 2017, on the 17th of August, gravitational wave was detected. So we will maybe come back to this. And after that, one could also position the source sufficiently nice so that optical telescopes could look in candidate galaxies for such nova stars. And actually this is the one which was then found in the galaxy NGC 4993, I think. So this event in optical, in the photon, was then called AT2007 GFO. And here you have snapshots of the time evolution, August 22nd, August 26th, August 28th. And you see how the brightness fades. So there's a light curve involved. The intensity of the light goes down. And this is what a good theory should also then predict, the light curve of such a kilonova. So, and here we have corresponding theory. So we have then we have the evolution, and this is actually the theory, and so two theories and compared with the observation. Okay, our conclusion from this section that these compact star mergers are presently the believed site to form the very heavy elements in the lanthanide and actinide region. Now I come to my final part of the lecture for today. Let us return to quark deconfinement. So, boiling QCD. So what do quarks have to do with all these element synthesis? So yeah, there's one thing which we have actually published last year in Nature Astronomy. We found out that the deconfinement of quarks could be a mechanism for exploding supermassive stars. So far, the supernova theory could not explain how stars, let's say of 50 solar masses or heavier, how they could explode. The standard supernova theory mechanisms were working for stars up to about 20 solar masses. And later on, the neutrino-driven supernovas could not explode in the computer. And we have shown that phase transition could drive also massive star explosions. Okay, and this is basically the main plot of this publication. We considered a progenitor star of 50 solar masses, and this is the phase diagram of QCD, temperature and density, and here we have the coexistence region of hadron and quark matter. At low temperatures and densities, here is nuclear matter, and here is quark, gluon plasma. And the black line here is the trajectory which a collapsing supernova takes. So we look at the function of time, how the central density and temperature in a supernova collapse evolves. And this, it meets here the phase transition. So then in the very center, and this is here actually also such a time plot, we have here first shock, and then evolves a very compact star center here of about 100 kilometers. This is the so-called proto-neutron star, which is still hot but very dense. And when we hit here the phase transition, then actually in the very center, quark matter can be formed. It has much higher density. So then you have to imagine that the density profile of the evolving supernova has a very high density in the center. Infalling material can be reflected at this density threshold. And this reflection is a shock. And here you see what a shock means. That means that at this collapse time of a little bit more than 1 second, then the radius of the star blows up here by several orders of magnitude. So here we had just 10 kilometers, and this is 10 to the 4, so 10,000 kilometers. And this happens here at about the speed of light, and then later on it still continues expanding. And this is a successful supernova explosion. And as a result, we have very entropy-rich material here, and this is a remnant, and here forms the proto-neutron star of about 10 kilometer size. And important for this is such a behavior of pressure versus density, that we have such a phase transition like in the characteristics of boiling water, that you have a liquid and a gas phase. Okay, here once more what star evolution tells us as the endpoint of stellar evolution. We have such an onion-shaped star, progenitor star, with an iron core. And this iron core, when it grows up to a mass of the so-called Chandrasekhar instability, it has then about 1,000 kilometers. It's like a white dwarf. Then it starts collapsing. Then there's a first elastic bounce. And when in this bounce the phase transition happens, then we can also explode the rest of the star. So this is how such a supernova explosion can be pictured in the phase diagram, temperature versus density. So, and here we show also the electron fraction, so the asymmetry of the matter. And this black line shows us where nuclei play a role. So at the highest temperatures and densities, there all the nuclei get destroyed, and we are back with nuclear matter. And actually here at very high densities, then we enter the phase of quark matter. Okay, I will not speak about the general. So this is the standard mechanism of which is neutrino-driven for supernova explosion. And this neutrino-driven mechanism works for progenitor stars here up to 20 solar masses. Then there's a gap, and still it works for a few stars like 25, but not for more massive stars. Yeah? And the standard supernova explosion mechanism produces then remnant stars, neutron stars, which are in any case lighter than 1.6 solar masses. So one cannot understand with the standard supernova mechanism how more massive neutron stars are formed. Like we know that there are pulsars with 2 solar mass, like David Alvarez showed you in his lecture. And here our new mechanism can help. So actually we can produce stable neutron stars here in the range of 2 solar masses. And and now this is our quark matter equation of state. It is built on a confining interaction model for the quarks here with such a string type potential which rises. But I will not go into the details of this, you can ask me. But and here, this is the typical mass radius curve of a hadronic star. And here is a phase transition, and due to our quark matter equation of state, we can also produce hybrid stars with a mass actually exceeding 2 solar masses. Okay, and so this is our this is a usual supernova event without phase transition. The trajectory would go to the black hole, but with our phase transition, then here, when we enter the phase transition, here the evolution changes, and here happens the second shock and the explosion. Okay, and this was the picture I showed already. There's an observable signal of this. So when there would be near enough such an event, we should measure after a first neutrino signal, then also a second neutrino signal, which comes from the deconfinement. So this is our predictable signal. Okay, and here you see the evolution of the mass of the protoneutron star. And this neutron star here can form actually a mass. This is the baryon mass here of 2.1. So masses of 2 solar masses are possible in this mechanism. Now, final part is there a possibility to form quark matter in the merger events? So this is a colorful picture of such a merger event. This is a pre-merger stage when you see slight deformations of the neutron stars, so-called tidal effects. Then we have the violent merging, and after that we have this kilonova when elements are synthesized and a light curve is generated. So this was the observation in gravitational waves. So we have observed for this GW 170817, we have observed the in-spiral gravitational wave, which is this chirp. So, David, did you sing the chirp? No? Okay. Yeah, so these gravitational waves make sound, yeah, in a sense. You can, this is the frequency. The frequency of 50 hertz. So 50 hertz is what we have in the alternating current in our plugins. And this makes a sound like and so we start here with and then comes the chirp. Is so this is called a chirp. So you can, I think you can make this also with this. So when this is also an example for a chirp. Okay. Unfortunately, after that, here the frequency went up to from 500 even to in the kilohertz domain, and in the kilohertz domain, so at about 2 kilohertz, we expect the typical frequency then of the post-merger gravitational waves. Unfortunately, the LIGO experiment was not sensitive enough to see gravitational waves here from the post-merger. However, if in the near future, and LIGO has just started a few days ago, the next round of science measurements, if there will be a next neutron star merger event nearby enough, then we might see the post-merger. And what can we deduce from that then? Okay, and this is what I would like to come to now. So here, just a short repetition. Binary neutron stars were known since the 70s. So Hulse and Taylor have got the Nobel Prize for the detection of such a, also called after them, Hulse-Taylor double neutron star system. And one of them is seen as a pulsar, and one can see actually then the period with which they encircle each other. And this period drops. So the period becomes shorter and shorter, as one expects when energy is lost by emission of gravitational waves. So the dashed line is a prediction from general relativity, from Einstein's equations, and the dots are the observed points. And you see how precise the predictions from Einstein's theory for the emission of gravitational waves are. However, this is only an indirect measurement because at that time gravitational waves could not be measured. Only now, since a few years, we are in the state that we can explicitly measure these waves which go through space-time. And this was the Nobel Prize of 2017, actually. And yeah, so here you see it looks a little bit like a disease here. This is the region in a merger event where actually the heavy elements are formed. So this, the people, my colleagues, like to speak of making gold, because gold belongs also to these heavy elements. Although gold is not the typical element which we would like to point out, more the lanthanides and actinides are the important elements which otherwise cannot be formed. But okay, so here it's colored a little bit like gold, because gold is formed in the merger events. Now, back to the hypothesis that in such a merger events where we form the most massive and hot neutron stars ever in the universe, if there can be a phase transition to quark matter in neutron stars, it should be there. But is it visible? So, and here we have recently written such a paper with Andreas Bauswein with our quark matter equation of state. So here you see the equation, one of many equations of state in the mass radius plot for different hadronic models. And there's one model here, this green one, with a phase transition. So here it deviates from the black hadronic behavior. Here is the phase transition. And the green curve here is how the maximal density in the merger event evolves. The black is without a phase transition, and the green is with a phase transition. With a phase transition, we can form much more compact cores of the protoneutron stars. And this is the gravitational, post-merger gravitational wave signal. You see the intensity as a function of frequency. In a hadronic star, so this black curve, the typical peak frequency is a little bit above 3 kilohertz, and we see a clear shift of this peak frequency when we form quark matter. Because quark matter is more compact, and for a more compact object, this is like a bell. Yeah? When you have a big bell, you have a low frequency, so a deep tone, and when you have a little bell, you have a high tone. You have a high frequency. So that's this one. Yeah? When you have a more compact object, the tone which you measure in gravitational waves is higher, the frequency is higher. And this is our prediction. Here all the crosses are for models where the equation of state has no quark matter. So the peak frequency as a function of radius of this protoneutron star lies around this line. With the phase transition, we have the green point, which is far off. So it's really a detectable signal. So here again, the same thing when we replace this axis by lambda, the tidal deformability. This is a quantity which we can also measure now in gravitational waves, namely in the in-spiral phase. This is a pre-merger gravitational wave, and this is a post-merger gravitational wave. When we measure both, we can make such a point in the diagram, and when this point lies on this band, we can be sure that we have had an event where there was no quark matter involved, at least no strong phase transition, and if it deviates, then we have a detection for the first time in astrophysics of a deconfinement phase transition. And with these nice perspectives, I would like to conclude here. We have new roads to explore massive stars and actually to make definite predictions how possible phase transition to quark matter could be seen. We have the fact that very massive pulsars are observed to solar mass could be related to such a progenitor scenario which involves very massive stars like 50 solar masses. We have an additional neutrino burst in a supernova, and we have a characteristic gravitational wave signal. And with this, we can place these astrophysical events like supernova, neutron star mergers, and neutron stars in this phase diagram of QCD to explore this rosa region of the nuclear to quark matter phase transition. Explain a little bit with a few formulas and also a bit say about compact stars, because that is a topic where we are working in Dubna and in Wroцlaw to neutron stars or compact stars as sites of the very high density, and where we explore possible signals of phase transition to deconfined matter. So, okay, the basis of this is Einstein's equations, which correlate space-time here with the Einstein tensor and matter with the energy-momentum tensor. So these are tensorial equations, so there are many components. So these indices, mu nu, are two-dimensional indices. So you have a matrix where this mu and nu goes from 0 to 3. So these are 4 by 4 matrices. So 4 by 4 is 16. Then by symmetry reasons, you can reduce this. So what we discuss here, so maybe first we should have an understanding of how matter and space-time work together, and the basis is these Einstein equations. And one of the examples how to solve such equation is that we take spherical symmetry, so here like a sphere, and Schwarzschild matrix, so this is a spherical symmetric ansatz for the space-time matrix. This is how to measure distances in space-time. So here, by the existence of masses, there is a modification of the time in the vicinity of the big mass and of the radial distance measured. And this is the angular. So angular dependence is by in spherical symmetry not modified. And when we would then determine the elements of the Einstein tensor for this matrix, you can read them off and then calculate this curvature measure on the left-hand side. And on the right-hand side, for the energy-momentum tensor, you take a diagonal matrix where you find the energy density and the momentum and the pressure. So then this T mu nu is something like epsilon minus P minus P minus P. And here it's everywhere zeros. So this is how in the solution of these equations then reduce to such equations where pressure and energy density appear. And I have colored here those terms which come from the general relativity. The black one is what all this reduces in the classical Newtonian case. So here you recognize Newton's gravitational force, and this is the pressure gradient. So this is the equilibrium between Newton gravitational force, the black one, and the pressure from the matter. And this determines then the stable configurations of compact stars. And here you have now corrections. And these corrections, so the red ones come from the equation of state. So when pressure is of the similar order as the energy density. And this means, look, the energy density goes like mass density, rho times c squared. And when pressure usually is much less than, so rho is mass times density. Usually terms like mc squared, they are much larger than what comes from kinetic terms. However, when you compress the matter very much, then we have heard yesterday about the Fermi gas and the Fermi momentum. And this Fermi momentum can be of the same order as, so Fermi energy, same order as the rest mass energy. And then the pressure, the resulting pressure, is of the same order as the energy density, rest mass energy density. And then these corrections become sizable. And the green one comes from the deformation of space-time metrics. And here let us make a little estimate. We have heard that the typical neutron star has a mass of up to 2 solar masses. Now, the Schwarzschild radius, RS, is 2 GM. And for the solar mass, RS of the mass of the Sun is 3 kilometers. Okay. When you insert here now a neutron star with 2 solar masses, what is the Schwarzschild radius? Oh. No. 6 kilometers. Yes. It's just look, you have this equation. When m is the solar mass, it's 3 kilometers. When m is twice that, it is 2 times 3 kilometers, 6 kilometers. So. Okay, so we have 6 kilometers here. And then when you remember mass radius curves, and I think I have here one, yes. So here we have mass radius curves. So a typical radius at 2 solar masses is 12 kilometers. So you have here 6 kilometers, here you have 12 kilometers. That makes 1/2. So you have 1 minus 1/2. What is this? 1/2. And then you have 1 over 1/2. What is this? 2. So this, sorry for being so elementary. So this green term makes for massive pulsars a factor 2. So this is an estimate of what you have to expect from general relativity when you calculate neutron stars. So therefore we need for theories involving neutron stars, and in particular massive neutron stars, we need general relativity because it can be effects up to, so alone from this factor 2, and this adds another, all give some positive contributions. Yeah? Okay. And here I would like just to demonstrate how it is important to have a theory for neutron stars to learn about the equation of state of matter. So on the left-hand side, the equation of state is given as pressure versus energy density. So actually, what is this relation between pressure and energy density? So for the blue line is a very simple equation of state. It's just the ideal gas without interactions, just neutrons. Neutrons are very important. Already Landau has considered them because when you don't have electromagnetic forces involved, it is just the gravity which would keep the neutrons together. And in the classical work from Oppenheimer and Volkoff, 1939, this example was calculated. They took this equation of state, put it into this Tolman-Oppenheimer-Volkoff equations. That is the name for this colorful equation. And the solution is this mass radius curve. Look here, the blue one, for free neutrons. And what you see is, here is one solar mass. They cannot even explain the existence of neutron stars with one solar mass. That's very bad, because we have mass measurements. Typical neutron stars have what mass? Did you remember? What is a typical? 1.2. Yeah, 1.2 is actually the lightest neutron star ever measured. So we have no knowledge about neutron stars which are lighter than 1.2 or 1.15 or so. This is the lower limit. And the upper limit is 2 solar masses. So in these limits, we know masses of neutron stars. Typical mass is of this Hals-Taylor pulsar, for instance, 1.35. Also, the same mass is involved in the merger event of the 2 neutron stars, which we have measured. So, lesson is free neutrons cannot explain the typical neutron stars as we know them, because the mass ranges from 1.2 to 2, so here. And this theoretical curve does not go into that region. So we should improve. So what is missing? What is missing in the ideal gas of neutrons is interactions. And which part of the interactions is important? It is the repulsion. It is the fact, which we have discussed yesterday, that the neutrons are not point-like objects. They have, in any case, a hard core. They are like billiard balls a little bit, yeah? So when they come close to each other and high densities, then they repel each other. This is a nonlinear Blaschke model. So this is some field theoretical model for compact star matter, and this is already performing much better. This has more repulsion. So you see here in the equation of state, at a given energy density, we have more pressure in the green curve than in the blue curve. So when we increase energy density or density, then we need much more pressure to reach a certain energy density. Yeah? So you can read this diagram like this. For instance, to reach an energy density of 1 GeV per cubic femtometer for an ideal neutron gas, you need just something like 50 or 60 MeV per Fermi cube pressure. But in a realistic case with interactions, you have to apply about 10 times that. Yeah? So much more pressure because of the repulsive interactions between the neutrons. So it's much more difficult to compress realistic neutron star matter to a certain density. And since this is so, the gravity will not be able to compress matter so easily and lead already at a very light systems to a gravitational collapse, because here what goes down is the onset of the gravitational collapse, the maximum mass, and this part is the part of stability. And because of the missing, pressure from the equation of state against the gravity, the free neutrons collapse very easily. Okay, so here the lesson is the observation of neutron stars in this mass window tells us that there must be very strong repulsive interactions among nucleons in the equation of state. What is SQM? SQM stands for strange quark matter. So this is a simple model of actually proposed by Witten, also earlier, that there could be a absolutely stable state of matter at high densities, which consists just only of quarks. So up-down strange quarks could form a neutral form of matter. So strange quark matter, so up, down, and strange quarks, they have a charge of up has plus 2/3, the down quark has minus 1/3, and the S quark has also minus 1/3. If we, for simplicity, assume that the masses can be neglected or all are very light, then you have a system just of up-down strange quarks with same numbers. Then this is electrically neutral, such a system. And so it is another example of matter which is just bound then by, or which then is not subject to some electrostatic repulsion or so. So neutral matter. And but in the difference to the pure neutron gas, the quarks have very strong interactions, attractive nature. So you could form a strange quark matter droplet, if it exists, in principle of arbitrary size, also very small size. So there could be so-called strange quark nuggets of a centimeter size or millimeter size, or micrometer size. And one has tried to find them, in particular in astrophysics. If something exists in nature, it should exist in astrophysics. So how to see this? Yeah, difficult. Yeah, and so they could not yet be found. However, it's not excluded. Yeah, and the idea is the following: if you plot again our energy per nucleon, like we did yesterday. And we have here this minimum, so this was the normal nuclear matter as a function of density. And at some point, there could be a phase transition. And maybe it could be like this. So we had yesterday discussed the case that here is some quark matter. But we don't know. Eventually, the strange quark matter could be subject by interacting, attractive interactions to form here such a minimum, which is actually less than the minus 16 MeV of the big nuclei, of the nuclear matter. And then this state here would be energetically preferred. However, there's a barrier, and this barrier keeps our world alive against tunneling into such a strange quark matter state. It's good that this barrier is there. Eventually, of course, as an alternative, it could look like this. Yeah, most likely it looks like this, and there's no danger. But if there is such a minimum, then once you are able to compress matter, then you can populate this state of matter. And because of this stability here, there could then be macroscopic clumps of matter of this kind. Strange quark matter, therefore, can exist here. This is radius. The radius can go to 0 here. So it can be very, very small nuggets, can fly around. Yeah?
Question.
Yes?
What if you create this minimum in the Nika collider?
Yeah. This is something like the black hole scenario in the colliders. Yeah? Yeah. Okay. Then the question is, what would a nugget do with the remaining matter? Would it, like a very hungry dragon, eat up all the other matter and then swallow the whole world? Yeah? So it's not, there's not an instability involved like with the black holes. Although these mini black holes, which have been suggested to eventually be formed in colliders, this was a big misunderstanding. We can discuss this later. Here, there are always, look, when there's one atomic nucleus, it's a very tiny object. Yeah? So if you form then from collision of two nuclei a little bit of strange quark matter, and this would fly somewhere, so the question is, what does it do in flight? Yeah? So will it how will it be detected? So there should be eventually some decays into observable particles, which show some net strangeness. Yeah? Because here we have strange but not anti-strange. Yeah? So it should be matter which has a quantum number strangeness, and so there should be typical decays and seen in the detector. But there were no indications yet for this in heavy ion collisions. Okay, yeah, but people have calculated this with models of perturbative QCD, and they find also here that they can reach also the mass range of two solar masses, actually in similar radius. So it's a competitor model for explaining massive compact stars. There are arguments against it which have to do with the fact what happens in a strange star at the surface. So because we know rather well emission of light or luminosity and of neutron stars, and if there were strange stars with bare surfaces, this should all be a bit strange, and there's no indication for this. Okay. Here, as a solution of the Tolman-Oppenheimer-Volkoff equation, you find not only mass radius, you can also plot mass versus the central density. Here, these three example equations of state compare like this. So when the mass rises with density, this is the stable branch, and this is the maximum. And after that, you add mass, but this leads only to a bigger compactification, so to a higher density. And when you are more compact, then because the gravitational potential is negative, you lose mass. Yeah? Because in the gravitational energy is negative, then you lose mass when you're more compact. And this is then unstable here. But the free neutron gas has the highest densities. So this you should contemplate a little bit. Why? Because under their own gravity, so the density in the center piles up the most. There is no force, no repulsive force, which could prevent that the matter in the very center of such a configuration gets very high densities. Yeah? This thing is different for the realistic model of nuclear matter. There we have the repulsive forces, and the repulsive forces, they prevent that in the center of such a star, this is the central density, the density can exceed to high values. Therefore, the maximum, after this is gravitational stability, this maximum is reached at about half the density here. But for that, we can load more mass onto the star because the star is not so compact. It has a larger radius also than this one. And therefore, there is not so easily the danger of gravitational collapse. Okay, and where do we stand? Then here, the real program would be, dear astronomers, please measure this mass radius characteristics and measure it very precisely. And then we can distinguish what is the true equation of state. So we can practically, from measuring mass radius, we can infer to the pressure versus energy density. So which of these equations of state is the correct one? You could tell when you would know mass radius for, let's say, many stars with many masses and many radii, then you can measure a line which would one-to-one correspond then to the equation of state. And this has been, of course, followed by theorists a little bit. So they analyzed measurements of radii and masses from bursting sources. And what they found is then here such a band for mass versus radius, which translates into such a band in pressure versus energy density. It's too good to be true because there are problems with these radius measurements, unfortunately. We have, at the moment, they are running new experiments for measuring the radii of neutron stars. So if we could, also from the gravitational wave, we have information now about masses and radii, and then we can reconstruct what is the true behavior of this mass radius curve. Once we know that, we invert the Tolman-Oppenheimer-Volkoff equation and can practically measure the cold equation of state of matter. And so this is a fantastic perspective for neutron star physics, that you can, with these objects in astrophysics, you can measure the properties of cold dense matter, which are inaccessible in laboratory experiments. Because in the laboratory experiment, we have the big nuclei. By definition, they sit at the saturation density here. But how to go to higher densities? When we perform heavy ion collisions, we have discussed this yesterday, we can compress the matter, so we can go up here, but at the same time we also excite the matter and temperature appears. And so we can not really measure in the laboratory this curve, the cold nuclear matter equation of state. So this one. But with neutron stars, we could. But we need very precise radius measurements, radius and mass measurements. So this is the zoo of different theories for how mass radius curves could look like for different equations of state. And you see how important it is to have good measurements. If we measure the mass alone, like this one here for this pulsar, the 2 solar mass, we can exclude already all the lines which do not reach 2 solar masses. This already selects out all these equations of state which are too soft. Also part of the strange quark matter equations of state. When you imagine that now a radius could be measured, let's say somewhere in the range between 12 and 13, then all these, I think these equations of state here, these ones are also out already from the merger event, which constrains the radius at 1.4 solar mass to a value of 13.5. So all what is here on the right-hand side is excluded. Okay, so the quality of these measurements will increase in the future, and then we can really extract from astrophysics the equation of state of dense matter. Okay, and this is how it presently looks like. The mass radius plot here. We have these dashed regions are from the gravitational wave measurement in spiral. There is possibly a maximum, the upper limit on the maximum mass here. There is a lower limit on the radius for this mass, a lower limit, an upper limit for the radius here. So you see an equation of state must go through this window, and it should not exceed here this mass. So something like this. And now we are waiting for new measurements of the radius of objects like this in the mass range of 1.44 from NICER. And first rumors are out, but they are not yet for public. And then we could further constrain in this mass in the mass range what the radius should be. Good, David.
When you come to free neutrons and strange quark matter.
This one? Mm-hmm.
Yeah, the mass radius. Can you make a model where you start with the free neutrons and then you come up first transition into the red one?
Oh. Okay, there are crazy colleagues of ours, actually name Dragon, Alessandro Drago, and he has an idea that the nuclear matter should look like this, so predict in this mass range very compact stars, and that this strange quark matter actually could go a little bit like this, and that we have a transition from more compact neutron stars to strange quark stars, which are more extended. I personally am very skeptic for how such a transition should happen, because the transition should be in accordance with laws of thermodynamics. At least in equilibrium thermodynamics, you could not understand this, such a transition. And he claims that there could be non-equilibrium transitions, like here, that for some time you can let a star live somehow on this curve of nuclear matter before it actually can make the transition to strange quark matter. And but then still the puzzle is, because here this strange quark matter lives at a higher density than here. So you must imagine this somehow like, I don't know, so like a transition from here to here. So I should draw this a little bit more like this. So then from here to here. Okay. And that state could be metastable. We know that when you boil water, you can overheat it, and here we can overcompress the matter, and it takes some time for the quarks to nucleate and to form actually then macroscopic regions of strange quark matter. That is the idea behind such models. Of course, the life of a theorist is very interesting because he can generate ideas, and sometimes it's very difficult to disprove ideas. Finally, they should be disproven by observations and by experiment. But in any case, I would welcome you all in the family of theorists who generate ideas, and sometimes crazy ideas, which give a hard time to your colleagues to disprove you. But this makes life interesting.